So just now we have seen the principle of the effective stress, and we'll move ahead with the capillarity in the soil, and this is closely linked with the previous chapter, which is the effective stress. So as far as your effective stress is concerned, so remember this concept is again attached to the effective stress principle as follows. So the capillarity is nothing but a phenomenon by virtue of which there will be a rise in the water level above the natural groundwater table, and therefore the soil will be remaining in the fully saturated condition. So therefore, so if I got the ground level, so this is the ground level, and if I got the groundwater table, and the soil below groundwater table is called as the saturated soil, remember, and the soil above groundwater table is considered as a dry soil or moist soil, so depending on the degree of saturation. But because we have the groundwater table, so there is a zone, or there is a tendency that in between the two successive soil particles there will be a creation of the small void, and because of this creation of the small void, water in the groundwater table will rise up to certain level. So I consider this as generally be this level. So this is the rise in water level, and this is nothing but the because of the capillarity. This is the same phenomenon as in you have studied in the fluid mechanics. What you have studied in fluid mechanics is very simple. You have taken a beaker and with full of water in it, and you have inserted a small diameter pipe. This diameter is very less. So because of this pipe insertion of the pipe, there is a rise in the level of the water, either rise or fall depending on this nature of fluid. So remember, so there is either rise or fall. Since in case of soil almost we talk about water, so we'll deal only with this rise phenomenon. We'll not speak about the falling of the, because fall is only possible in case of the mercury, you have seen. So similarly, as I said, we'll discuss only about the rise because it's water. So in water there has to be rise. So this zone up to which the soil is saturated by the capillary water, this zone is called as the capillary zone, and the soil in this zone, remember, is fully saturated. So this soil is fully saturated. This is very important, and I'll derive the expression of the rise in the capillary tube H with the surface tension properties of this fluid. So it is very easy to, or I'll call it is very simple derivation. So if I insert just the tube, so the water will be rising and it will form a concave shape, and as shown in this figure, and along this perimeter of this tube there is a force called as a surface tension force acting around its perimeter. So it's the sigma. So this sigma is acting all over its perimeter. This is the sigma, surface tension force. This force is acting uniformly. That means the force is not changing as you're moving across or along this perimeter. This is surface tension force. So this force is making an angle equal to alpha with the vertical face of the cube. So this is in plan, and this is the elevation, I'll call. So in plan it is looking like this, and this is the diameter of the tube, which is very small. This is diameter small d, So therefore you've got first of all this force. First one is the surface tension force sigma, and second is the weight of water or fluid in the tube. You've got all this, and just you need to balance this weight of the fluid in the tube with the surface tension. So this has to be in equilibrium, system has to be in equilibrium. So therefore the total weight in the tube, first of all, is very easy to calculate. Total weight of water in the tube. And how to determine this total weight, which is nothing but just gamma density into volume, and volume is nothing but the volume of the tube. So that means volume of this, that means volume of this part, only this part. It is nothing but pi by 4 small d square into h. Very easy. Pi by 4, I'll consider diameter of tube as small d square into the height h. So this is how the weight is calculated in the tube. Second is the surface tension force, which is responsible for pulling this water, which is responsible for pulling up the water. So by virtue of the surface tension, you've got up with this capillary phenomena in the soil. So therefore that force is nothing but surface tension force into the area at which it is acting. So by looking at this figure, the sigma is surface tension force which is acting all around its perimeter. So therefore perimeter becomes the acting area. So therefore it becomes sigma into perimeter, which is nothing but pi into d. So these two has to be equal, this one and this two. So by equating equation 1 and 2, you will get gamma w into pi by 4 into d square into h equals to sigma pi into d, and pi will get cancelled, d will get cancelled. Okay, there is nothing left to be cancelled, and therefore you'll get the height, which is height of either rise or fall, becomes equal to 4 sigma divided by gamma w into d. So therefore it becomes equal to the capillary rise becomes equal to the 4 sigma divided by gamma w into d. So this is again very important expression of the capillary height rise in the soil. So this is capillary height rise, and in all normal cases for water, sigma is equal to 73 millinewton per meter. So this is milli, m, small m is milli, M-I-L-L-I, milli. So therefore if I just place all the values in the units of the Newton and meter, you'll probably get h in terms of the d. So it becomes capillary height rise equals to 73 into 10 raised to minus 3 into 4 divided by 9810 into d. So you will get, so you need to place remember d in the meter. So if you evaluate all this factor, you will end up h equals to no, not the point, it becomes equal to 3 into 10 raised to minus 5 divided by d. But remember you need to place d in the meter. So if you want to place d in the millimeter, so you'll get h equals to 0.03 divided by d, and remember here you will have to place it in the millimeter, and this is how it is related. But one more thing, this is the capillary height rise. So if you just reduce d, you'll get more and more capillary height rise. So as d reduces, h increases, and vice versa also true. As d increases, h decreases. So therefore I'd like to make 3 important points. In the next slide I will do it. So first point is that, So if you got the capillary zone, suppose this is the capillary zone, this is capillary zone, and this is the height rise h, this is the existing groundwater level, and below which the soil is totally saturated. About up to capillary zone, it's also saturated. So whenever you got the capillary height rise, so up to the height equals to h, so there is a tension, a lot tension into a negative side. So there you got the tension, and beyond which there is a compression. So here it's compression. So because the water is pulled up, so that means it's under a tension. So I will define a tension by negative and compression and positive. So in soil mechanics, compression is positive and tension is negative, a sign convention basic, and in your strength of material, tension is positive, compression is negative. So it actually varies, sign convention varies from one subject to the another. For as far as your soil mechanics is concerned, remember whatever who is in tension, who is in compression. So you have taken u as negative because you have taken gamma dash, which is equal to total stress minus pore water pressure. So if this pressure you have considered it is in the compression, right? So therefore if you're going beyond this groundwater table down, you just need to consider it with the positive sign. But in case of the capillary zone, where you are end up it at the tension zone, this u will become a negative. So once u becomes negative, the sigma will become equal to minus of minus u, which becomes sigma plus u. So therefore this is the expression in capillary zone. So which means in capillary zone, effective stress increases. Point number one. Point number one, in capillary zone, sigma dash increases. Point number two. Point number two here is very important and a very crucial point. You have seen I've considered small d over in this denominator part. So this d is not the diameter of the grain. So this d is not diameter of grain, but d is the size of void. Exactly, because it is ultimately a void or the diameter of the void which is created in between the two adjacent soil particle, which is responsible for the rise in the capillary, and so which is responsible ultimately for the capillarity in the soils. So but obviously this void size, this is the void size, obviously this void size is related to the particle size. So this is the particle size. So there is a relation between void size and particle size, and that relation is given by the Terzigian pair. It is as follows. Generally, that what they have also given, the diameter of the I'll call d void or size of a void is directly proportional to the void ratio of the soil into the effective grain size of the soil to a constant c. Obviously they have termed this c is the empirical constant, So after introducing this empirical constant, I'll remove this proportionality sign and I make it equals to. So if you place the d void in your or existing capillary height expression, you'll end up at getting h equals to the 0.03 times the which is existing is 0.03 by d, which is in mm. So I'll just replace it like this way. H is direct inversely related to d, and I just need to place d over here, because which is nothing but d void or size of the void, and capillary height will in turn becomes equal to c divided by e into d10. So this c is which takes into account of this 0.03 factor, and it is empirical constant. It varies in between 0.1 to 0.5, and E is the void ratio obviously, and D10 is the effective grain size. We have studied it in the soil classification chapter, which indicates that the 10% of the soil is finer than this particular size. This is effective size of the particle. So obviously it is a grain particle. So this is again an empirical expression given by Terzaghi and Pick. This expression is given by Peck is the student of Terzaghi. So rewrite this spelling Terzagh, Terzaghi and Peck. So Peck is the student of Terzaghi, and Terzaghi, as you're aware, it is the father of the soil mechanics. So this is the point number 2. So first point, in the capillary zone, because of the tension, effective stress increases. So this is point number 1. Point number 2 is the clarification about the diameter of the void or the size of the void, which is again related to the final effective grain size diameter. Based on the same point number 2, I will introduce the third point. This table particularly is given by Hans Boe in 1975, which gives a clear identification of the coarse-grained soil and as well as the fine-grained soils. So as you are aware, and also we have seen it in the soil classification chapter, we've got the broadly 2 classification, which is nothing but the coarse-grained soils, and we've got the fine-grained soils. So in fine-grained soils, we've got the sills, we got the clays, and in coarse-grained soil we got the sands, we got the gravels, and obviously other soils are also there, boulders and cobbles in coarse-grained soils. So based on this soil classification, Hans Boe in 1975 has given a table which is purely an indicative of the type of the soil and type of the type of the soil and the capillary height, right? So here it is a type of soil. So he has considered coarse sand, fine sand and medium sand. So first is coarse sand, and here it is a capillary height edge. And in continuation of these 2 points, I am highlighting this third point, which is very, very important. So as because in second point also we have seen the edge, which is nothing but I'll bring that particular point over here. In second point, we have seen the capillary height rise edge is nothing but C divided by E into D10, and obviously which was inversely related to D. Capillary height rise is inversely related to D. So there is a direct relationship between this void and the particle size. So as you decrease particle size, D void will go on increasing. That's what is also been researched by the Hans Boe in 1975. He has given this table. So So for coarse grained, particularly for coarse grained soils, for coarse sands, the capillary height ranges in between 0.03 to 0.15 meter. It's fairly arranged. It's medium sand, then we got the fine sand, we got silt, after all finally we got the clay. So for medium sand, this range is in between 0.12 to 1.10 meter. For fine sand, it's 0.3 to 3.5 meter. For silts is 1 to 10 meters, and for clays it is more than 10 meters. So for clays, you have seen, as your particle size goes on decreasing, the capillary height goes on increasing. So that's what is again highlighted by the Hansbo. So remember, for third point, if the size decreases, if particle size decreases, capillary height increases. So particle size and obviously d10 is directly proportional, so therefore this decreases, this increases. Similarly, the particle size decreases, h also goes on increasing, because particle size and the diameter of the voids in the soil are directly related. So we have seen the concepts related to capillarity in soil. So we have seen major three concepts. First, because of the capillarity, the effective stress goes on increasing, and second, we have seen that it is not the diameter of the grain which is influencing the capillarity, it is the diameter of the void which is ultimately, or which is responsible, or ultimately the diameter of the grain. Repeat, we have seen the not the diameter of grain is responsible, it is the void or size of the void which matters, which is directly proportional to the capillary rise in the soils. And in third also we have seen the same extension of the second point, and also the clarification given by scientist Dr. Hansbo in 1975. And now we see the practical application, or where it is going to be applied it in the field. So probably you have gone into the couple of visits into the nearby seashore. So nearby a seashore, so I'll draw a section. So I consider this as a sea. From this point there are the waves which are coming up in the, so probably you have visited to the nearby offshore or onshore areas where you see this whole diagrammatic representation, and this is the water table or water level in the sea, and as you go on this you get into deeper and deeper sections. So this water level in ground, I'll join it by like this way. So since you got the very fine sand near the shore, so you got the very fine sand near the shore, this is very fine sand. So because of this capillarity, what is done is that see, you've got the fine sand, right? And because of it is very fine, it has got a capillarity which is ranging from 1 meter to 10 meters, obviously. So therefore you got a zone of the capillary action, and because of this zone of the capillary action, this particular soil is held it in a tension. So because of the water which is in tension, this particular soil, you're probably can able to walk, can able to have a good ride only at this portion. But after this portion, once this portion goes into that end, so you've got only the dry sand. So barely you can able to walk on, barely you can able to run on this soil. So it is very difficult to run on this particular type of soil because you've got very poor strength. So therefore here you've got very poor strength of the soil, and in this region only you've got the good strength because of this capillarity effect, because of only this capillarity. And hereafter we are not bothered. So obviously because it's in the submerged in the water, you've got the poor strength in the soil after this point. So this is the region where I'm interested in. So this region is only because of this capillarity. So this is the particular application of this capillarity in the seashore, nearby or seashore areas, where you got the very good quality soil, and also you can able to run, you can able to walk, or you can able to play around this soil. And this is a theoretical explanation because the capillarity is linked to this concept. So this is the first application. Second application, or the second terminology, is nothing but capillary siphoning. So in this concept I'd like to have some more clarification about the earthen dam. So remember, in earthen dams what is done, you build a core at the middle of its, or at the heart of the dam. So this is the core, and generally the core is made up of the very impermeable soils like clays and silts, and here we got the coarse grained soils all around the core. So normally once you start retaining the water on its upstream side, this is the upstream side and this becomes a downstream side. So what happens, the water will start percolating through this core, and because you have got or placed the very impermeable soil in this core, so the infiltration rate, or the rate at which the water is moving, is very less. So we have got this phreatic line, and we probably get very little amount of water in the downstream. So water is percolating and there is a flow of water through this particular type of the soil. So what happens, because of this this particular type of soil in this side, after the core starts, because of this soil there will be the zone of the capillary action. But remember, this zone is only restricted to this level. So but what happens, because of this particular height in rise, what happens, the siphonic action will happen, and more amount of water will be pulled to downstream end. So this is a very serious issue. So this is very serious issue, because the drawing or siphoning action will increase the flow rate, and therefore in the practical situation it is done it in the Berlin. So this, because of this siphonic action, they have observed the rate which was around 2000 liter per minute, and this rate was brought down to 450 liters per minute by increasing the height of the core just by about 0.1 meter, just by about 0.1 meter. So this is the practical example of the capillary siphoning. It's a very special case, and it's a very practical one, because you have seen just the normal siphon, but the siphon happens because of the capillary action as well, because the water, once the water, where you got the path, the water will move out and trace, and will find and will dissipate all its energy. So remember, the water which has got the very high strength, and it's find its way by deteriorating all the civil engineering structures. So this finishes your the total capillarity chapter, and we'll discuss the permeability of the soil in the next chapter. Thank you.